Hello science fans. Today we are talking about control systems. Control systems help us manage other systems. They command, direct, or regulate behavior. Think about your home thermostat. That is a control system. It keeps your room at just the right temperature. Cruise control in a car is another great example. It keeps your car at a steady speed. Control systems are everywhere. They make our modern world work smoothly and efficiently. Control systems are like the brain of a machine. They take information, called input. Then they make decisions based on that input. This decision leads to an action, called output. The goal is to keep something at a desired state. This desired state is often called the set point. For example, your desired room temperature is the set point. The thermostat works to match the actual temperature to this set point. Imagine you are riding a bicycle. You are a control system. Your eyes see the path. This is your input. Your brain processes this information. It decides how to steer. Your arms then move the handlebars. Now, let's talk about PID. What does PID stand for? It stands for proportional, integral, and derivative. These are three control terms, or actions. Together, they make up a PID controller. A PID controller is a very common control loop feedback mechanism. It is used widely in industrial control systems, and in many other applications too. It continuously calculates an error value. This error is the difference between a desired set point and a measured process variable. The PID controller tries to minimize this error. It does this by adjusting a control input. The P, I, and D parts each react to the error differently. The proportional part looks at the current error. The integral part looks at the sum of past errors. The derivative part looks at how fast the error is changing. Each part plays a unique role in the control strategy. Think of them as a team of experts working together. They all focus on getting the system to the desired state. Why is PID control so popular? Well, it is quite robust. Let's start with the P in PID. This stands for proportional. The proportional component is all about the present. It looks at the current error. Right now, the error is the difference between where you want to be, set point, and where you actually are, process variable. The P controller's output is directly proportional to this current error. So, a bigger error means a bigger response. A smaller error means a smaller response. It's quite straightforward, really. This provides the primary driving force for correction. Imagine you are steering a boat towards a dock. If you are far off course, a big error, you make a big turn. If you are only slightly off course, a small error, you make a small turn. That is how the proportional controller works. It provides an immediate reaction to any deviation. The strength of this reaction is determined by a gain factor, Kp. A higher Kp means a stronger reaction to the error. However, a Kp that is too high can make the system unstable. It might oscillate wildly around the set point. Section 4, I for integral, remembering the past. Next up is the I in PID. This stands for integral. The integral component is all about the past. It looks at the accumulated error over time. If there is a small persistent error, the integral term will grow. Eventually, this pushes the system to eliminate that steady state error. There is a small, steady gap, and they keep gently pushing the boat, little by little, until it finally touches the dock perfectly. Section 5. D for derivative, predicting the future. Now, let's explore the D in PID. This stands for derivative. The derivative component is all about the future, in a way. It looks at how fast the error is changing. It calculates the rate of change of the error. If the error is changing quickly, the D controller provides a strong response. If the error is changing slowly, its response is weaker. The main purpose of the derivative term is to add damping. It helps to reduce overshoot and oscillations. It makes the system response smoother and more stable. Imagine you are driving a car and approaching a red light. You see the light, the set point is to stop. If you are approaching it very fast, the error changing quickly, you brake harder. If you are approaching slowly, the error changing slowly, you brake gently. The derivative controller acts like this. It anticipates where the error is heading, and it tries to counteract rapid changes. This helps prevent the system from swinging wildly past the set point. Section 6. PID in the real world. Engineering marvels. PID controllers are not just theory, they are everywhere. Mechanical engineers use them in so many applications. Consider HVAC systems, heating, ventilation, and air conditioning. PID controllers help maintain the perfect temperature in buildings. The P part reacts to how far off the temperature is. The I part ensures the room eventually reaches the exact set temperature. The D part helps prevent overshooting, so it does not get too hot or too cold. This ensures comfort and saves energy. Robotics is another huge field for PID control. Think about a robot arm in a factory. It needs to move to precise positions, quickly and smoothly. PID controllers manage the motors in each joint of the robot arm. P helps move the arm towards the target position. I corrects for any droop or steady error due to gravity. D smooths out the motion, preventing jerky movements or vibrations. This allows robots to perform delicate tasks with amazing accuracy. Automotive engineering also relies heavily on PID. We have already talked about cruise control. Section 7. Tuning PID. The art of perfect control. Having a PID controller is great, but it needs to be tuned. Tuning means adjusting the P, I, and D parameters. These parameters are called gains, Kp, Ki, and Kd. The goal is to get the best performance. You want minimal overshoot and no steady-state error. A poorly tuned PID can perform badly. Tuning is both an art and a science. Engineers often start with manual tuning. They make small adjustments and observe the response.